about source of uncertainty. I'm not saying the water quality models doesn't have any of them either. They do have a lot of uncertainty in a lot of our assessment. But one of the nice things about some of the modeling capability that if you could develop proper models, they could help you in terms of identifying where to monitor, when to monitor, what to monitor, and how often to monitor, for example. Okay, just to answer those simple questions, because we talked about under various conditions, whether it's a dry condition or wet condition, or initially after a small rainfall versus large rainfall, how the bacterial loads are different, actually. So models can help you to inform an awful lot of information that you may otherwise may not be able to assess other than shooting in the dark, for example, going collecting every sample that you can get and what you can find from that, actually. So what I'm going to talk about is to just give you a brief overview of various different models out there and their functions or their roles that they can play. And the major limitation, I'm not saying models are perfect or models are ready for the prime time yet, actually. Still, it has got a long way to go. If you look at the models over the last 40 years, when they are developed over the 40 years, we are still struggling what we think we know about, say, sediment or nitrogen and phosphorus. We are still studying after 40 years, actually, struggling in over a 40-year period. But bacteria is something very, very new phenomena. Pathogens, emerging contaminants, we are looking at hormones, we are looking at pharmaceuticals and so many different factors, actually. All these are all very, very new phenomena, new concept, and it's going to take even longer for us to get it working well, actually. But nevertheless, there are some key important processes that the model can develop that can inform you and that can provide you some useful information that could be incorporated in your PSD source tracking. So that's what I wanted. Just touch base on some of those stuff and maybe try to enlighten some of the work that's going on. In general, water quality models can be classified into three major categories. One is just a statistical-based model. Whether it's a spatially explicit or non-explicit doesn't matter sometimes, depending on how spatially variant or how heterogeneous versus homogeneous the area that you're looking at, for example. Some other thing I listed there is the LDC, low duration curve, or ArcHydro. ArcHydro is not a model, it's more like a database management system, okay? And then, of course, Select. Karthi will talk about more extensively, so I'm not going to go into detail there, actually. Then Sparrow. Sparrow is a USGS spatially regression models to look at the water quantity and quality issues. Then there are models such as mass balance. So as the name suggests, it's going to just give you what's input and what's output. Okay, it does not able to translate what's happening along the way, actually. Okay, the transport, the fate and transport of different media, whether it's the water, soil, air, whatever it may be going on, actually. So it may not be able to show you those real reasons, but all it can give you is what maybe the total input from the watershed may be and what may be as an output, as a simple decay process and things like that. So these are all some of the models that are related to the mass balance. Then finally, you have more deterministic or mechanistic models that are most widely used for various purposes, including lots of TMDL, watershed protection plan, and so on and so forth. And some of them are HSPF, SWAT, SWIM, and WASP. WASP is more of a reservoir model with a stream and reservoir hydrodynamic model, whereas HSPF and SWAT is more into the landscape and watershed scale models. Then SWIM is more of an urban watershed, actually, okay? Urban landscapes, if you want to call that. So those are the various different kinds of models. Like as I said, each one can play an important role in informing you or in assessing the impact of the various sources of pollutants that includes pathogens, okay? Like as I said, the spatially explicit statistical models can tell you more about what are the potential sources. Okay, if you say there are X number of animals or X number of wildlife, okay, coming up with those numbers is difficult, actually. All we have is the county numbers, and that numbers are assessed once in 5 years, okay? We just talked about what Kevin and Terry did in one of the watersheds where you're rotating your animals in and out, actually. We don't have anything of that detailed information for every farm and field where the animals may be getting in and out of the system, actually. So all we have is the county numbers. So all the spatially explicit tools can tell you is exactly what are the potential sources if there are animals, n number of animals in that, and different age, species, type, and so on and so forth, actually. Okay? That's all those models for, basically explicitly spatially allocating load on the landscape. Okay? And then the mass balance models can provide you some additional information, such as, okay, if those are the input, okay, what do you expect as the potential load that may be getting discharged to a river, for example? Okay? So that's how far you can do. Whereas the mechanistic model or the deterministic models can take one step further. It can tell you both spatial and temporal variability on a daily time step or a monthly time step, depending on how you know the management of those particular units, whether it's the domesticated animals or whether it's a wildlife or whether it's a point source or anything in between, actually. Okay? Because when you start putting all these different sources together, there is a lot of interactions going on, actually, both on the landscape level, also at the stream level. So if you are talking about the complex environment, then definitely you may want to consider something more mechanistic. But at the same time, the data requirement and the knowledge need to do a deterministic model is not that cheap, or that's not that easy either, actually. It's very complex, okay? So I just want to alert you about the overall concept of the various models. Then we can go into more detail. I don't expect you to read this. I just want you to know the same model classifications, spatially explicit models, the mass balance models, and the deterministic models over here. Okay. What are the functions each one of them can do based on the type of classification? Whether you're looking at the sources, what are the different courses, like watersheds versus rivers versus lakes and reservoirs, freshwater, estuarine, or what are the stuff used for TMDL type of analysis, and whether it's a one-dimensional, two-dimensional, or three-dimensional, as well as the time scale, whether it's a steady state or time variant analysis. Plus, you can look at the watershed characteristics, rural versus urban, and then the in-stream processes, then waste load allocation and the load analysis. So there are various ways you can classify these streams and see what they can do, actually. You can see not any one model is going to do all of it, obviously, okay? Each model has got certain strengths and weaknesses. So this came out directly from the BSD task force report, actually. You might have seen that report, and you might have realized that, actually. If you want, I would recommend you to look at that report on more detail about each model, what some of the strengths and limitations, and where you can apply it. Currently, for most of the work that's done in Texas, okay, we used a combination of these models. Mostly, SELECT is almost used in almost all the watersheds. I won't say all of them, but most of the watersheds. Some of the UT analysis has used the arc-hydro concept with a simple one-dimensional decay. And in some of the other models where you don't have enough information, such as you don't even able to develop a low duration curve, for example, then we use a more deterministic model to just estimate the stream flow, okay? Thereby, you can use those stream flow to estimate your load duration curve and look at the load allocations, whether it's a wet weather or the dry weather, what's causing the most of your load in the watershed and things like that. So it's not, the models, the way it's used currently is not used to its fullest core strength, actually. They are all used as a anecdotal or additional information that can inform the process in which the bacteria, the pathogens may be transported from a landscape to river bodies to estuarine or lakes and reservoirs and so on and so forth. Okay. I mean, you all know already what are the various sources of this water pollution, actually. Obviously, nutrients, the pathogens, and the sediment are all associated with water, okay? It's very straightforward to get data out of the point sources. You can go and get a point source coming out of a pipe. You can go and sample them and quantify them and whatnot. But what's not known is, even though the point source is, may say, completely free from pathogens. Okay, we all know there is plenty of E. coli in the general environment, actually. But the pathogen, the point source can provide the source, or the food source, or the nutrient source for the pathogens to grow. So as soon as that pathogen, the point source comes in contact with the river, whatever the natural background E. coli that may exist in there could multiply, could grow and die on a certain time. So if you start talking about a 1 mile or 2 mile down the streams, what is the impact of those pathogen transport, for example, or how they multiply, or how they die off over the time period and things like that. So still, there is not a whole lot of research that can able to really quantify the effect of point sources, not directly on pathogens, but indirectly affecting the growth and die-off of pathogens in the stream, for example. And of course, non-point source is more difficult to identify and control. Okay? If you're talking about nitrogen and phosphorus, there are various ways in which you can able to control them, either chemical treatment or physical management and practices and things like that. Whereas pathogen is not that straightforward to control. Okay? If you're doing the water WPP, or if you're going to be doing any kind of TMDL analysis, one of the things you have to do is load allocation and the implementation down the road. Actually, how are you going to control this problem? Now that you identified the sources, now you have identified the load that may be coming from the various sources, how are you going to control those sources actually? So that's not very easy, or that's not very straightforward to do that actually, and pathogens is a lot more difficult because of the way in which they can persist. Okay, they can die off, they can be go in an incubation period for some time actually, then they can emerge back again actually. So I was intrigued by what Mike presented yesterday about the soil actually. You had to thaw the soil under various conditions, you can still find a lot of pathogens growing in those situations in Minnesota, for example. So it's not an easy way to control non-point source. The best way to control non-point source will be at the source itself. Okay, once it's let out of the source and goes into the stream, it's going to be a lot difficult for us to manage and maintain the pathogens. Okay. Again, there are various potential sources actually, but most of the people are attributing the pathogens is from the domesticated animals or the wildlife animals are the major sources according to the US EPA report actually. But the animal feeding operations have been cited one of the major source for the adverse effect on the environmental and public health because of the high rate of land application of manure increases the risk, which I guess most of you already validated or verified that based on your BST data set actually. But again, what we are still not sure is how much is the existent. Okay? So if you take 1 kilogram of dry manure or wet manure or fresh manure, how much of bacteria is in each one of them actually? Okay? And what kind of bacteria? Because each bacteria behave differently, transport and transform differently actually. Still there is a lot of unknown questions. If you want to really truly want to model this stuff actually, we still have a long way to go to analyze and understand the various sources of bacteria and their abundance and availability under various conditions, including temperature, carbon sources, soil media, as well as water media, and so on and so forth, actually. So that's what I'm trying to say. Unfortunately, the current technologies is not adequate to handle some of the large treated areas, actually. And sometimes these can build up over a period of time, like, again, what Kevin and Terry are showing there, actually, that they may be there in the soil or in the media for a long period of time, actually, and then they may reappear at a later stage. So even if you thought you are controlled at the source, that could be in a reservoir that may be staying there for quite a long period before it comes out and able to cause problems in the downstream water bodies. So the general approach in most of these models, is especially the deterministic model, what they do is they take the existing model, because already these models are fairly good in terms of assessing quantity of water runoff, the sediment transport, sediment pathways, as well as the nitrogen and phosphorus, actually. And of course, some of them can do pesticides and other sources. But now we are adding a lot of new tools or new science and new equations to those models to add bacteria or the pathogens. Because we are not able to model all pathogens, we just use a general classification of persistence versus less persistent. Okay, where persistence may be something like E. coli or one of those higher order bacteria, whereas fecal coliform could be a less persistent bacteria. So you have two sets of equations or two sets of mathematical formulation in these models that can try to carry forward a generalization. We may not be able to track by species like you all able to do in the BST, where is it coming from animal or is it coming from human versus whatnot, actually. All we can able to do is we can combine all those sources and at least able to quantify how much is ending up in the river, what's happening when it goes through a lake or a pond or a reservoir, what happens 5 miles down the stream or 10 miles down the stream. So using a simple decay approach, actually, again, there's a lot more work needs to be done to really understand how the dilution and the decomposition or the diffusion of those bacteria is happening along the river of the system. Sometimes you have to know what is across and in depth. So you can be, it's a one-dimensional model or two-dimensional model or three-dimensional model. Depending on the type of models, those processes can be simulated and able to inform you the various sources of the pathogens as they come in contact with the water bodies, for example, actually. So what are some of the major components the current deterministic models can perform? Obviously, hydrology, a comprehensive water balance. Most of the models can do the water balance pretty good right now, actually. And some of them can do the sediment fairly well also. But then once you start coming into the nutrients and pesticides and other stuff, then you start to get lesser and lesser comfort zone in those outputs, actually. That's because the nature of those constituents are very complex to model and monitor and whatnot. But the most important thing is, in any model that you want to choose, we want to make sure it can represent the various management, land management. That is the key. Okay, what is models for us? Model is abstraction of reality, right? So if you want to represent the real world in a more proper way, you got to be able to make the management. So whether you are doing a no-till versus some kind of a tillage operation, whether you're going grass versus regular pasture versus switchgrass, or whether you're going corn versus soybean, how all these going to management practices is going to affect the assimilation or the deposition or the diffusion of your pathogens is very key here, actually. If your model is not able to represent that, most likely you're not going to, all you can get is a more lumped assessment of what may be happening in your watershed, but you won't be able to differentiate between field A to field B, for example. Okay? Your soil with a clay soil versus sandy soil, you may not be able to represent that very well if your model doesn't have even a soil component in your system. So you got to be making sure the environment, the media, the sources, and the fate and transport, all these things are all fairly well represented in any model before you could choose that model to make any detailed assessment. Okay? Then, of course, you want to also look at one other thing that we are looking at, not only just the bacteria, we are looking at a lot of hormones, pharmaceuticals, emerging contaminants at the request of EPA to look at the whole suite of things, actually, of how you can look at some of the organics and the inorganics that may be transported through the water and soil and other medias. I'm just giving you one model. In this case is SWOT, which is more closely associated with that, actually, just to give you a complete and a comprehensive water balance that you need to capture, actually. Almost all deterministic model would capture this type of information, both spatially and temporally. When I say temporally, I'm talking about whether it's a daily or sub-daily time step, or whether you're looking at spatially means every field by field, or a sub-watershed level, or at the basins level, depending on whatever the resolution that you're interested in, your model should be able to capture most of these processes. So as you can see, the rainfall is your major source of major driving factor, and then as soon as it hits the ground, it's going to be divided into runoff versus lateral flow. And whatever that is excess in the soil is going to go to the groundwater, which could return as a groundwater flow or what is called return flow back to the river. Okay. So you ought to be able to capture at the various processes or the fate and transport pathways. Okay. So when you're talking about runoff, there is going to be sediment associated with that, whether that sediment coming from the landscape versus through the lateral flow or through the groundwater flow. All those things can be tracked, and thereby, if there is any pathogens or any pollutant that's going to be associated with it, whether it is a nitrogen, phosphorus, or emerging contaminants, those could be transported also at the same time. So that's one of the reasons I said at the beginning of the talk, it's very important, just not, even if you don't believe in these models, whether they can do a really good job of pathogen or not, just having this information of the sources, okay? Especially when you're developing the LDC, the low duration curve, or where you're going to develop any kind of the select process that Karthi is going to talk about later, you got to know how much of your runoff is directly from the field, and how much is coming from the lateral flow, and how much is coming through the return flow or the groundwater contribution, actually. Okay? So that can help you to decide what you want to monitor actually, and when to monitor, and how often to monitor actually. So you may not need to be spending a lot of resources in going collecting the same data over and over again, and that may or may not be fully informing you anything additional other than confusing the whole matrix that you all showed in the last 2 days. So this could, or a day and a half, this could help you at least to isolate what to monitor actually, okay? So we have done lots of analysis on the pesticide. Just like your bacteria, pesticide is a very expensive process of monitoring and analyzing your data and things like that actually. So that a lot of work has gone through in the water quality model to assess how best to monitor actually and what to monitor. So that has been very informational or very good standard practice to use the models to inform you how to monitor, how to design your protocols and monitoring program, and so on and so forth. Okay. So, what are some of the fate and transport of pathogens or any of most of the contaminants? Most of them is going to be from the surface loadings. What's coming off of the surface runoff and sediment and so on and so forth actually. Some of them are going to be direct sources to the streams, whether it's a wildlife like feral hogs or whether you're talking about the point sources and so on and so forth. But a lot of the things depend on how easily those pathogens can attach to something. Okay, whether it's dissolved into water or attached to sediment or attached to organic matters, how does it transport actually? Okay, so still there is a lot of research or work needs to be done on this area to really understand how they attach and detach from various particles and how they survive in those media actually, and what are the real food sources or the nutrients that make them survive actually, or make them multiply, or make them die off at certain point of time actually. So you still, the absorption coefficient and the runoff extraction coefficient, when I say coefficient, these are all factors, okay, these are all processes actually, not just one number. And then of course the enrichment coefficient is what's happening in the sediment, okay, how much is attached to sediment. Then finally, how are they decayed, okay, in the soil, streams and the reservoirs and so on and so forth. So in a deterministic model, this is how the model is represented right now for the pathogen actually. Either it is a less persistent or persistent pathogens, we are looking at the application of, let's say, manure. Okay? When you apply, that's already a crop or a pasture land or whatever, that's a chicken manure or as a cow manure or whatever that you're dispersing, you could be applying directly on the land that could be intercepted by your leaves, or it could be directly applied on the landscape before the planting season, for example. So what happens to those applications actually, some of them can dry and die off directly from the leaf, and some of them can wash off during a rainfall, and it can go to the soil, and whatever that's in the soil can infiltrate and degrade inside the soil or leach to the groundwater, or some of them can attach to the soil and water particles and directly deposit it to the streams. So this is how the current deterministic models handle the various pathways for the pathogens that's getting simulated in a watershed model. So I'm going one step further here. Actually, if you look at those bacteria processes, so here you can look at the application of manure, for example, and when that's applied, okay, so it's applied to the land or on the soil directly or on the plants, like I said. And that could be, when it is on the plant, it's got certain portions on the plant itself, and some directly reaches the ground. And once it gets to the ground or on the soil, they can die off or grow further actually, depending on the source of nutrients and the availability of water and soil moisture and so on and so forth. But the current model assumes only it's going to wash off if it is at least 2.5 millimeters. That's 1/10 of an inch, basically. Okay, when the rainfall is at least 1/10 of an inch, then only we expect that to be washing off from the leaves to the ground and whatnot. Whereas what's applied directly on the soil can be absorbed by the sediment or the soil particles, or some of them are soluble in the water system actually, under the moist condition or under anaerobic conditions. So that sorbed in the soil can die off or grow in the soil based on the availability of nutrients, and then move through the sediment. Then whatever it's in the soil solution, like in the water solution, can move with a runoff on the overland or subsurface or leach to the groundwater. So this is how the current model setup at each parcel by parcel when the watershed model is applied. This is how the current processes are simulated in a deterministic or a complex models. Okay? I can tell you right now there are very, very few TMDL application that uses this entire complex processes. Whether you're using HSPF model or the SWOT model or SWIM or any other model for that matter, there are very few applications and the US-wide has successfully applied this model because it needs a lot of data, a lot of field monitoring information to really quantify the various processes before that model can be used in a more confident manner or more with less uncertainty and so on and so forth actually. I know there are 2 or 3 TMDLs in Missouri has used the SWOT model. There are a couple of, I would say 4 or 5 more in West Virginia or Virginia. BPI guys have used the model. And North Carolina has done some of this modeling work actually. In Texas, we are mostly using more on load allocation side, actually using the select model process, which Karthi will talk about it in the next presentation actually in more detail. So once you get this bacteria in the various sources or various media, how are we going to handle that actually? In other words, how are you going to change the bacteria in the soil media, for example? I should stay away from this. Oh, okay. No, I don't think so. So the bacteria that gets dissolved can be removed through either runoff or the leaching process actually. And whatever the bacteria that is transported can be transported through some kind of media, whether it is a sediment or organic matter, because organic matter can become a source for a lot of this bacteria to grow and able to reproduce much more faster than some of the other media actually. So we had to take into account both of them, how the bacteria is survives in the various environment actually. Once the bacteria arrives in the stream, what happens to that actually? So there is some kind of a dilution, the decomposition or the decay process that happens in the stream, but sometimes we also have lakes and ponds and reservoirs. Those may be trapping some of those bacteria sources actually, especially the sediment sources. So as the bacteria or the sediment attached bacteria settles in the lake or pond, it's going to take away the bacteria along with that actually, and it may have a long reservoir resident time in a lake and pond. Again, I'm going to a little more detail than I would like to, but here it gives you some of the transport equations, how the model is done. So you got the deposition, adsorption, extraction from the runoff, and the sediment extraction, and finally the decay process. So each one of them are simulated at each field by field actually. Okay. Again, in order to do that, you have to have the detailed management of what's been done to that field in order for you to really truly be able to process some of these stuff, then eventually what's happening in the stream processes. Okay. So I'm giving you a very, very generic on one model here actually, but most of the model have a similar set of equations. The parameterization may be slightly different, but the general processes is still the same, such as the deposition, adsorption, extraction from runoff, sediment, as well as decay process. Okay. So for the degradation in the stream, we use the first order kinetics, and there is a different rate at different solution phase and different absorption phase, whether it is in the soil that is attached to sediment, or in the soil solution phase, or if it is on the foliage or on the leaves of the plant material, or if it is in the stream, or if it is in a pond and reservoir. So everything has got a different resident time and different fate and transport equations actually. They are not all the same. Okay, that's what, and also they change by the type of soil actually. It's not that one equation sets for the same for all different types of soils actually. So by the type of soils, if it is a clay soil, you may have a lot more absorption coefficient than the sandy soil, for example. Okay, so each one of them will be different here also. What I'm going to talk about next few slides is just to show you how we are working with USDA ARS, Agriculture Research Service, to collect a lot of field data that helps us to validate our model and also understand the various processes and the pathways of these pathogens. Okay. So in Beltsville, Maryland, the USDA ARS has set up a nice field where they are applying manure at various rate and also I know a lot of you mentioned about, oh, we had to wait for Mother Nature, actually. So we simulate our own nature by rainfall simulator. Okay, so we have our own rainfall simulator that simulates simulate various quantity of rain, various intensity of rainfall, various application rate, various vegetation, like whether you're growing grass versus corn versus pasture versus different cropping system, different soils, media. So everything is changed here with a simple setup here. You have different types of soils. Then we also have the output that's collected, both the runoff and the subsurface flow and the groundwater contribution, actually. So we try to track every one of those sources from the various sources to find out whether we are able to reproduce some of these, what we are observing here through the modeling system. Why are we doing a lot of this stuff, actually? Again, we're going back to the original exercise because you cannot go and monitor your BSD source tracking in every possible places, actually. So if you have your model set up and if you have the confidence in your model and the systems of equations and the mathematical formulations are well represented of various pathways, probably, okay, you may be able to reproduce the same experiment through the modeling system to really find out what's going on, actually, and especially accumulating all this stuff, what's happening in the landscape, rather than just doing 1 or 2 field experiments. So here is the actual setup that you can see. That's a rainfall simulator, actually, that rotates and sprinkles water. So you have all the way from no crop or no vegetation, just applying manure on the barren land, to all the way to the various crops that are grown on the landscape. So it's a very small plot. It's not a very real case study where you're having a farmer's management and things like that, but we are trying to simulate or mimic, and thereby we can collect data into 1 or 2 years rather than waiting for 10 years to get 2 rainfall events sometimes, actually, 2 good rainfall events. So, like, again, as I said, it's done in Beltsville, Maryland, but in the USDA ARS research site. And that's Ali Sarahi, who's the principal investigator of this project, who collects a lot of the data. You can see this is the rainfall simulator. As it rains, actually, they can go and collect the data at various soil profile, actually. Okay, so we get the runoff, the base flow, and the lateral flow from all the different sources. We get both under vegetation and under no vegetations. Again, it's a different setup that it shows you where the data is getting collected at different time of the different time. And also, we don't stop only just collecting the data on the water and the soil, on the sediment, but also we are trying to put the probe in there, actually, to find out how the bacteria moves in the soil profile. Okay, so you can find out after, say, 6 inches or 12 inches how the bacteria may have moved along with the water or solution or whatever the different media on the face. So those data are also collected in this one to really test and validate the hypothesis in the modeling system, how well it's represented. The next couple of slides, I'm going to just show you quickly some of the model results. So here is pasture. This is all E. coli under different manure application rate. Okay, so here is for the pasture land, and here is under corn field, actually. I'm not showing all the results here. We have data published in a paper. I can share that with you. And this is the model prediction. Okay, the solid line is the model predictions, whereas the dotted line are the data collected at different sites. Even though it's the same pasture land, but the data were collected at different locations. Within that, you can show the variability, how even though it's the same field, same application rate, same thing, but you got at different rates, actually, in which the sampling shows, actually, depending on the slope, depending on whether you're looking at the top of the soil versus the bottom of the field, and so on and so forth, actually. So the data is collected at multiple locations. But you can see it's fairly, I mean, for modelers, this is pretty good, actually. So I don't know what you say about your other system, but it is pretty good in terms of modeling. You can say it's a 10 to the power 4 coliform forming unit per gram of soil there, actually. Whereas if you look at the corn, okay, that's 10 to the power 4. Here also it's almost 10 to the power 4, but it's a clear distinction depending on where you collect. Okay, this is the 3 separate SWOT model here, actually. Each one represents each processes at each slope of your landscape. Some of them are very flat land versus steepy slopes and the different soil conditions, actually. So that's what. So again, under all the 3 conditions, obviously the model is under predicting, except in the last one is a little bit over predicting here, actually. But overall, the x-axis here is the number of days of application. If you apply the menu at the starting day 1, for example, after n number of days, you are still seeing the bacteria in the water column and the sediment column and so on and so forth, actually. So that tells you some of the multiplication factors that's going on, or some of the survival factor that's going on in the system. The same thing, I don't think I'm expected to read that again. So here again, E. coli under con. Here is the fecal coliform. So these are the two different species. This is a less persistent bacteria in our model, and this is the persistent bacteria in our model, actually. The same way we are showing you for the pasture land. Okay. Again, overall, there is a general representation of what's really going on the field. Okay. This is just one study in one plot that's been done, actually, but this needs to be repeated. This is on a field scale level, but we don't have an equivalent scale in the stream. Okay. There is not much research going on in the stream. I saw some work done by the EPA yesterday, actually, so maybe there are some new data sets that may be coming out, actually. And as more data gets published and more growth and die-off curves for each of these bacteria get published, actually, we will be able to represent them through the mathematical formula in the model. Thereby, we may be able to simulate the different growth rate and the die-off rate and the different transports of fate and transport of the different bacteria. There are a few things I want to leave as this is my last slide probably, and I want to leave a few things actually. One is model is going to be as good as your input data set. I'm not saying the model is perfect. It's lots of uncertainty in our inputs actually. Just in a case, an example is what Kevin and Terry mentioned about how they collected the data. When they looked at all the samples, nothing's showing different actually. As soon as they saw the animal rotation, you start to see, you can easily decipher between what's contributing and how much the contribution is coming from the presence and absence of those animals in a particular field and things like that. So having a very detailed understanding of how this management operations on the field level is very, very important if you want to pinpoint exactly what's going on, and if you're going to be using this for WPP or TMDL analysis, then you got to be a lot more clear in terms of where the sources are actually. The model should become a part of your TMDL and WPP framework, but at the same time, of information that you may otherwise, it's very difficult for you to provide that information actually. So it the BST tool set or the toolbox that we all talked about in the last day and a half. Model should continue done, and we can walk. We are not quite there in terms of phosphorus actually. Maybe we are getting process, but phosphorus is still a very complex system. So we don't claim to have that every answers for pathogen transport as of now. So it has to evolve over a period. Funding needs to having a lot of field presented through decay rate is not manure, for example. Good kilogram of drug. Okay. Whatever it is. So step of input process in simulating in a mathematical, complex mathematical model like so forth. It's more detailed. It can increase the load going at one and is to really quantify how good is what is the confidence limit. There could be